Now it's time to look at light as a particle. We already discussed the experiments of the 1800s that demonstrated the behavior of light as a wave, including Young's double-slit experiment as one of them. But the theory that light also behaved as a particle was yet to be proven with evidence. This evidence came from Einstein, who proposed that light can behave like a particle, and he was able to demonstrate this concept so thoroughly that he actually won the 1921 Nobel Prize for it in 1922. It may come as a surprise to you that it was actually for what we call the photoelectric effect that he was awarded Nobel recognition, not for his theories of special and general relativity. The photoelectric effect is a demonstration in which a beam of light is aimed onto a metal plate, and electrons are ejected from that metal plate as a direct result of the light shining on it. This can be seen by connecting the metal plate to a circuit that has a second plate aligned with the first. As the free electrons begin floating off the first plate, they are attracted to the second. This flow of electrons from one plate to the other creates a current in the circuit, which is measurable. Notice that as the wavelength is changed, the amount of electrons that are emitted also changes, which can also be seen by observing the changing current measurements at the bottom of the demonstration. This is because the basis of the photoelectric effect depends on the suggestion that incident light comes in tiny packets called photons. Einstein theorized that each photon has a specific amount of energy, which is determined by its frequency. These photons can only kick off the electrons on the metal plate that have the right amount of energy. But how does frequency factor in with the energy of the photon? The frequency of anything is how often the thing happens in a given amount of time. In our case, the frequency of a wave is the number of cycles that pass a certain point in 1 second. So which of these two waves has a higher frequency? Look for the wave that passes through the line more often. If you're counting with me, you'll find that the top wave passes through the line 8 times for every 2 passes that the bottom wave completes. This goes to show that the wave with the shorter wavelength is the one with a higher frequency. Wavelength and frequency are 2 parameters of an electromagnetic wave that are related by the equation lambda equals c over f, where lambda is the wavelength of the wave in meters, c is the speed of light, since these are light waves that we're talking about after all, and f is the frequency of the wave in units of inverse seconds, which are often referred to as hertz. Let's use this equation in an example. We must determine the frequency of a wave of green light with a wavelength of lambda equals 540 nanometers. So we start with the equation lambda equals c over f, where c is the speed of light. We know the values for our wavelength and for the speed of light, so we replace those variables with their values to get 540 nanometers equals 3 times 10 to the power of 8 meters per second divided by the frequency. But remember that the wavelength should always be given in meters. So 540 nanometers is about 5.4 times 10 to the power of negative 7 meters once we have reduced the value. So now we have 5.4 times 10 to the power of negative 7 meters equals the speed of light divided by the frequency. Rearrange this equation to isolate f, and we get the speed of light divided by the wavelength of that green light gives us 5.56 times 10 to the power of 14 inverse seconds, which is approximately 556 times 10 to the power of 12 hertz, if we were to move the decimal to the right twice. The reason we do this is because the new order of magnitude that we have can now be replaced by the prefix tera for trillion, and we get about 560 terahertz as the frequency of this green light, keeping in mind that we have to present our answer with 2 significant figures, so we round up. Not only is the frequency of light dependent on its wavelength, so is the energy. The energy of a photon is defined as E equals hc over lambda, where E is the energy of the photon in joules or electron volts, both of which are units of energy that are frequently used in astronomy. H is Planck's constant, c is the speed of light, and lambda is the wavelength of that light. So let's determine the energy associated with a photon of UV light that has a wavelength of 115 nanometers. We start with E equals hc over lambda. H is Planck's constant and c is the speed of light, and lambda is our given wavelength. So all we need to do is plug in the numbers and do the math. The seconds will cancel on the top of the fraction, but we have to remember that the wavelength has to be in units of meters. So the product of the two terms in the numerator becomes 1.986 times 10 to the power of negative 25 joules times meters, which when divided by 115 times 10 to the power of negative 9 meters gives 1.727 times 10 to the power of negative 18 joules, since we previously canceled out the meters in the previous step. Now, since 1 electron volt is equal to 1.6 times 10 to the power of negative 19 joules, we can convert our answer from joules to electron volts, and we get 10.79 electron volts, which is approximately 11 electron volts. But our answer has to be presented as 11.0 because of the three significant figures that are required from us due to the number that was originally in the problem. So we can now see how the wave-particle duality of light makes sense. Some behaviors of light are like that of a wave, while others mimic that of a particle. So how do we summarize the relationships between the wavelength, frequency, and energy of light? As the wavelength of light increases, so does its frequency, but its energy decreases instead. This is because energy and wavelength are inversely related, meaning that if one is high, the other is low. For example, ultraviolet light has short wavelengths but high energy, whereas infrared light has longer wavelengths but a low energy.